interaction over the bandwidth and temperature here between the metal and the insulator. We have seen that within dynamic unit field theory, to which I will restrict myself in this talk, it means by taking a purely local set energy, you have the first order transition to the coexistence region where you can stabilize a metallic solution up to here and you can get an insulating solution from here on. So now, okay, this is the disclaimer. What we have not considered here are magnetic phases which are setting at low temperatures depending on the geometry of the lattice and so on. And we are looking at the space diagram from a local picture of dynamic unit field. You have also compared this to real materials. You have plotted, I believe, in function of, well, pressure or chromium doping, the phase diagram of vanadium 2O3, vanadium sesquioxide, temperature here, and you have realized that there is indeed a paramagnetic metal to insulator transition here as a function of pressure. And then, as we said before, at low temperature, this is covered by magnetic orbit. So you have kind of assimilated this one-band Harvard model phase diagram to this phase diagram. However, if you look a little bit more closely with the magnifying glass here, you realize in the real crystal there's something else. You have orbital physics. A priori in B203, you could have the 3 T2G states with 2D electrons. So here, this is plotted as A1G and EG orbitals. And possibly, this could play a role in the. I'll come back to this later. So let's go to the multi-orbital Harvard model. You have seen that also already. So you have a hopping term with a lot of orbital indices M and prime here now. Coulomb interactions, which can be more complicated. You can have Coulomb and Kunz-rule coupling. You can, in principle, have additional spin flip and pair hopping terms. And in principle, get more degrees of freedom. For simplicity, I got the spin flip and pair. Okay, I believe the first person who did multi-orbital simulations of the Harvard model in VLP was Marcel Rosenberg. As function here of U, and now the band filling, if you look at a two-band model, you realize that now you can actually get a mod transition. If you have quarter-field system, one electron in two bands, half-field system, or a three-quarter-field system, that means one-quarter-field whole system. And you have also seen the more modern version of this with the Janus phase in Lucas' talk, where he discussed the influence of Kunz-rule coupling J on this diagram and the metallic phases appearing in the text. So now you can ask the question, our initial phase diagram here with metal insulator transition and the critical use here, how does that evolve when I have a multi-orbital system? And as it has also already been mentioned, that indeed, I think this appeared first in a paper by Gunnarsson et al. In a qualitative fashion, and later on in various works, and where the more quantitative work here by Florence et al., that these critical use here increase with orbital degeneracy, either with square root of n, or actually with n being the orbital degeneracy. So then you get actually a phase diagram. So for the one-band Harvard model, it would be here, two-band Harvard, three-band Harvard, and so on, where you get an increase of the critical interactions in general.
Can you stay shortly why one is the root of n and why is n?
Okay, so one is the
the root of n is easy.
I'm sorry?
The root of n is easy, but why is n?
Okay. Okay, let's do that for coffee. Yeah. Okay, so now let me ask you a question. Let me go to the photo emission data of these D1 perovskite systems. Strontium monadate, calcium monadate, lanthanum titanate, yttrium titanate. These are all either perovskites or distorted perovskites with gadolinium iron 3-side distortions. They all have one electron in the T2G states. So the T2G triplet is the lower line manifold in this configuration, 3 T2G states, 2 PG states. And yet, the first two here, strontium monadate, calcium monadate, if you look here at the photo emission spectra, are correlated metals with a renormalized quarter particle peak here coexisting with the Harvard band. Whereas yttrium titanate and also lanthanum titanate, if you were looking at the really stoichiometric version, are actually not considered. Yttrium titanate has a large gap of about 1 electron volt. Tantalum titanate is just on the verge of the Mott condition. So what's happening here? Isostructural compounds, to first approximation, isoelectronic, but two are metallic, two are insulating, and somehow the most insulating is the huge gap. Why is that? Okay, let me give you 2 or 3 slides more of ingredients, but then I will ask you a question again. So these are the structures. Strontium vanillate, perfectly cubic perovskite, here have the vanadium atoms on the oxygen hydra. Strontium in the middle. Now, the distortion consists in backing up here that this, what was 180-degree just vanadium oxygen chain is buckling, and the angle formed by the vanadium oxygen bonds goes down in yttrium titanate up to 144 degrees. Okay, so some considerable structure distortion. The earlier band structure, of course, as you can anticipate, if you put 1 electron in 3 T2G bands, is always metallic. Again, my disclaimer, I'm not considering the magnetic phases. For yttrium and tantalum, you would have low temperatures that are cut off by ferromagnetic and ferromagnetic phases. I'm considering the temperature ferromagnetic phases. So for which band theory would always give you metal. 1 electron in 3 bands. Corresponding density of the states, well, here you can think that you actually start getting a hint. Namely, you see that between strontium vanillate, calcium vanillate, and the titanates here, there are 2 things happening. Well, you have a slight reduction of the bandwidth here, and you also have now the 3 T2G density of substates here that reflects the lifting of the degeneracy within the T2G manifold by the distortion. Okay, let me ask you the question again. 2 correlated metals, 2 insulators with very different gaps, 2 electron volt, 1 electron volt, and yet nearly isostructural and isoelectronic. What makes the difference? Okay, so nobody wants to give the obvious answer, namely that it could be that it's just the bandwidth reduction. We are buckling, so we are reducing the bandwidth, and in strontium vanillate we have a bandwidth of roughly 2.5 electrons for the T2G electrons, and in yttrium titanate we have 2 electrons. Nobody wants to give this answer because you're already smelling that I want to Okay, you could have thought that, so just bandwidth reduction. And if you look here at the experimental papers, obviously this is what experimentalists had in mind in the early days, plotting things as U over W, Coulomb interaction of the bandwidths, and showing you that band theory is getting worse and worse. However, what I will tell you, or what I will argue here, is that this is not the whole story. That what is important here, in addition to this bandwidth reduction, is that the crystal field lifts indeed the orbital degeneracy within the T2G states, and that this, enhanced by the correlations, suppresses orbital fluctuations, and you will actually end up with a system which has a reduced effective degeneracy. So I will argue that the titanates are more or less, in the end, one-band systems. Okay, let me give you some qualitative ideas in that direction. So with that, already at the level of a band theory, when we've got density of states, we have a certain orbital polarization induced within this T2G manifold. Well, that is of the order of maybe one orbital populated to 60%, 70%, but not complete. However, when we add the correlations, you can easily think that if you had a really large crystal field splitting, and a system with 1 electron in these 3 bands, if the upper 2 bands would be so far away that delocalizing those you don't gain any kinetic energy, you would just put your electron in the lowest band, you would have an effective 1 band form. So now the question is one of energy scales. So what should I compare? Should I compare the bandwidth of the system to the crystal field? Well, as pointed out by Manini et al. In this paper here, when you have the correlations, you're renormalizing your bands. So the kinetic energy gain is not the bandwidth, but it's the renormalized bandwidth. You have a quasi-particle residue z times your bandwidth. So you have a much smaller energy scale, and your crystal field splitting becomes much quicker, much more effective. So you can much more easily reduce this effect of degeneracy. And then, of course, if you have a system which is not a 3-band model, but just a 1-band model with 1 electron, well, then what I've shown you before, the critical U for a 1-band model is much lower, so it's much easier to write a 1-band system insulated. Okay, to capture that kind of physics, of course, it's not sufficient just to take a simple circular density of states and plot and put it in some dynamic machinery. We need now the details of the crystal fields, the hoppings, the different bands, the lifting of this degeneracy. So how can we capture this more realistic physics? Well, what I want to argue here is that we can put into the dynamical mean field calculations input from band theory, and here in this case from density functional field. So I want to give you an overview in 2 slides what is actually this density functional field, just really in a nutshell. So you may know that this goes back to 2 seminal papers by Hohenberg and Cohn and Charm in the 60s, where they were realizing that in principle the ground state properties of an interacting n-particle system can be formulated as functional of the density only. You don't need the knowledge of the wave function. What they did was to split up the in principle exact ground state energy functional here in the kinetic energy part, which is kinetic energy of an auxiliary system, which is non-interacting but of the same density as the system of the grid. Then the trivial parts like the energy corresponding to the external potential that you put your electron system in, the Parker potential, and the tricky part, which is essentially defined as being rest, comprising exchange correlation effects and also the correction of the kinetic energy term here. That means the difference between the kinetic energy of an interacting and a non-interacting. The nice feature about this split up is then that you can pass actually, kind of formally exactly, to a scheme where all this here is taken care of in a formalism where you would just have an effective potential and you come to one particle Schrödinger equation, because this splitting is just telling you that you have a non-interacting kinetic energy plus some terms that you can plug into an effective potential. Okay, so you have a one particle Schrödinger equation with one particle wave functions here. However, remember that these one particle wave functions are just used to parameterize the density. You cannot use those as really physical wave function of your system. So it's really an auxiliary system that we're solving here to get eventually the ground state energy. So then, as we said, the part somehow that we call the rest. Of course, we don't know exactly exchange correlation energy at this correction to the kinetic energy. But we can do approximations to that. I won't dwell on this issue because it's not central here. But the most common one and very successful one, which is used somehow in most electronic pressure calculation nowadays, to my understanding, is what is called the local density approximation, which constructs this functional, this unknown part of the functional based on a description of a homogeneous electron gas at the respective density of the different ones in the cell. Okay, then you have the ingredients, in principle, to do explicit calculations. So let me just summarize why or how I will use this theory here. So we're saying DFT achieves a mapping onto a separable system. That means a system where you just have a band theory with, however, an effective potential for which you have to make an approximation of the density approximation here. Strictly speaking, this theory is not for excited states. We have introduced this as a ground state theory. However, with these 2 caveats, I can just view it as a kind of mean field construction, or a kind of effective one-particle construction, which then I correct within, for example, the dynamical mean field scheme that you have introduced last week. So I use this construction not somehow in the density functional way of what I'm going initially to calculate the ground state energy and so on, but I use it to construct an effective one-particle Hamiltonian that serves them as the input for an electronic structure calculation. So that goes back essentially to these proposals of the groups of Anisimov et al. And Diefenstein et al. in 1980 to to combine density functional theory calculations by taking the LDA Hamiltonian as an input for a one-particle particle Hamiltonian, represented in a localized basis set. You add Hubbard interactions, Hund's interaction, whatever you want. You construct a multi-orbital Hubbard model, and you solve this in dynamic field.
That degeneracy works for multi-orbital case?
Yes. So this is what I want to convince you here. That we do this program, LDA plus MFT, for the four compounds that I've shown you. The thin line here is just the LDA density of states. And the thick line is the spectral function calculated from the MFT within this field. So now what you see is that indeed for strontium vanillate, you have the renormalization from this larger bandwidth here to the renormalized quasi-particle peak from levels at 0 here. And you split out spectral weight for the lower and upper Hubbard bands in the ratio somehow that you have one electron in these three bands. So that means the filling here is 1/6 of the whole spectral weight. So this is why this is so awesome.
If you use simple LDA plus U, would you also get same result concentrated?
No. Okay, LDA plus U, I think, can be viewed as a static approximation to this. So this will not describe me the coexistence of these low energy and high energy features.
But at least to give this vanadium system as metallic and titanium as insulated, would it give?
It would give this in the ordered phases. If you do the calculation in the ferromagnetic case for yttrium titanium, but it's not in this ferromagnetic sense here, because okay, let me describe first the physics and then come back to the question. So if you look here at the titanium compounds now, you see that indeed you open up a gap, quite small for the lanthanum titanate one, and of the order of indeed 1 electron volt in the yttrium titanate. However, these lower and upper Hubbard bands here are not associated to spin up or spin down or something. So it's really the ferromagnetic calculation. And to my taste, somehow this is the strength of MFT, that you don't have to suppose any kind of order to get these phases here in space. However, if you're of course interested in the zero temperature properties, you want to have the ordered phase, then you don't replace the
Silke, excuse me.
Yes.
Maybe this is the same question as Daniel's, I'm not sure, but can you tell us how U equals 5 EV was chosen and why the top and the bottom values are the same?
Sorry, why?
Why the top values and the bottom values are the same, since they're different ions?
Okay. This was essentially because it's a little bit early work already. So at that time, what we were thinking was that we were not satisfied with an explanation which would just put a big U on the titanates and a small U on the vanadates to get one insulating and one metallic. So what we were thinking is that the difference of U, even if there may be some small difference, should not be at the origin of the physical behavior. And this is what the calculation is.
So you did it on purpose.
However, yes.
Yeah.
However, in the last years we have worked a lot on how to really calculate U. So nowadays we try not to just take a parameter and go through a sequence. Okay, so that means LDA plus MFT gets indeed here the correct metallic behavior for the vanadates and the behavior for the titanates as insulating. You can compare the photon emission, so let me take for the strontium vanillate case here just the occupied part convoluted with the experimental resolution. You see that it's not so bad compared to this experimental resolution. Okay, and you can also analyze why actually the LDA plus MFT calculation is getting the titanates insulating. So what we realize is that you can find a basis where indeed one orbital is occupied and the other empty. Well, one orbital occupied means kind of 88% orbital polarization in the lanthanum titanate and 96% in the yttrium titanate compound. So that means you really do this scenario that I described to you. You polarize the system more strongly in orbital space by your correlations, and you go to a situation where essentially one orbital carries the charge, we have some orbital order, and then of course.
Can I ask a question? I mean, because of orthorhombic distortion, I think I understand that you lifted the degeneracy.
Yeah.
But it's between the dxy, and then the 1D orbitals are still degenerate, right?
It's Well, no, you have first of all, you have the T2G and
Yeah.
the EG
Right.
that's already in strong similarity. So now you lift further. So you
Yeah.
have the 3 T2G orbitals
Right.
which are split.
But three of them, because it's still perovskite.
No.
You have XT and YG is
It's not
degenerated.
exactly perovskite.
Oh,
It's
okay.
a deviation from the cubic perovskite that matters here.
So XT and YG are also
the
the.
gadolinium iron type distortion. So you really lift the degeneracy between the 3 T2G orbitals.
So XT and then YZ and then XY.
Well, it's superpositions of those, yes.
Oh, superpositions of
Yeah.
those. Okay, got it.
Okay, so now let me come back to a little bit more formal model. So what happens if I take a 2-orbital Hubbard model, but with the crystal field splitting? So just the model I did before, but with the crystal field splitting, and I forget about hybridization, I forget about J for a moment, and I look what happens as a function of this crystal field splitting, as a function of U, if I put one electron in these two bands. Well, one electron in these two bands. If there was no field splitting, you would at some point here, your critical, have a metal insulator transition. If the crystal field splitting is really large, then the electron will be in the lower level. It doesn't even see the higher band. So that means you will have the metal insulator transition at the U critical, which corresponds to the U critical of a one-band model. That's what I call effective degeneracy. Now the effective degeneracy is 1, not 2 anymore. And if you vary the ratio of crystal field splitting over the bandwidth, well, you have a line here going down like this, where you separate insulating and metallic behavior. And here you have a fully polarized insulator, fully polarized metal, whereas now you can, if the crystal field is smaller and not helped by you, go to a case where you have a partially polarized metal and up here, small area, a partially polarized insulator. Okay, so now let me come back to the vanadium sesame oxide case. We were saying here we want to describe this paramagnetic insulator, the paramagnetic metal regime. Again, both of these places are metallic in LDA. You have this time 2 T2G electrons, 2 electrons in T2G gas here. There were early ideas, I guess you discussed that in the second lecture with Matthias Reuter, that it was argued very early on that this should actually be kind of the mod transition in the one-band Hubbard model, because you could have a splitting here of A1G orbitals in a pair of vanadium. This would be filled, and then you would end up somehow with a spin 1/2 model effectively on these lines. However, this was questioned in 1999 in a paper by Yezhov from IDRSU calculations, and confirmed then 1 year later by measurements from the group Park et al., saying that no, indeed, this should not just be reduced to one orbital model, we should have here a spin 1. So what we did? Yes, well, we have 3 orbitals. Well, okay, let me show you. Wait a second. Okay. We did again this LDA plus DMFT scheme, and what we find here is the spectral function. The total one is here in red, which you can decompose into the A1G part, the green line, when you see you have very little occupation here, and the EG orbitals, which are more or less half. So you have now zeros approximation, 2 electrons in these 2 EG bands. Okay, how does that work? Okay, let me first show you the comparison to photo emission. That's not so bad. So this could indicate that we are on the right track. Also, if we look at the crystal structure of the insulating phase, we just open up a gap, so that is consistent. Let me get back to the paramagnetic metal phase then, and let me analyze that further. If we plot the self-energies here of the different orbitals, A1G here and EG, and I do this on the imaginary axis, because theoreticians like these imaginary axis behaviors, then I would, in Fermi liquid, expect a behavior that goes linearly to 0 at low frequencies. So now what you see here is, as a function of temperature, high temperature in red, low temperature in blue, in the A1G, you go from a behavior which, well, doesn't really go to 0, but starts to become linear, to something which gets much better here. So you could argue that somehow between these temperatures here, you're reaching the coherence temperature, or the coherent regime of the system. However, for the EG pi orbitals, as a function of temperature, not much is changing. You're still getting something which is of the order of 0.5 electron volt here, and that is the inverse lifetime of your EG quasi particle. 0.5 electron volt, it's gigantic, so you can ask the question, do I actually have an EG pi quasi particle at this temperature? So this is why we're saying here the EG pi actually stay incoherent down to our lowest. Let me skip this and furthermore, we can look now on the real axis at the real part of the self-energy. So here, plotted as this green line for the EG and for the A1G self-energies, terminable at 0, you see that roughly you're pushing the EG and the A1G in opposite directions. So what you're doing here is you're increasingly emptying the A1G orbital, filling the EG pi. That corresponds to the effective crystal field splitting that we have here. Effective field splitting enhanced by the difference of these two self-energies. And the effect goes actually from a mere 0.2, 0.3 in the band picture to nearly 2 electron volt when you add these effective parts of the self-energies. Okay, then you can plot spectral functions corresponding to that. Here, the thing you should notice that at 0 at the thermal level, you have the A1G band just still crossing. There's about 15-20% of occupation still here. And the picture that we have from the insulating phase then is that it's gradually pushed up and the EG orbitals form an insulating
If it would be indeed like that, wouldn't you expect very strongly anisotropic conductivity?
I would expect very peculiar temperature behavior because
No, I mean just anisotropes, because A1G are all along C direction, so, but experimentally it looks like this is more or less anisotropic. In this picture I would expect that conductivity in C direction would be much higher.
Well, I mean, in the metallic phase, I still have A1G occupation. So
Yeah, that's right, but if real quasi-particles are only in C direction, then I would expect that conductivity would be very strong anisotropic.
what means very
A1G is
strong?
symmetric orbitals. Maybe I didn't establish. The A1G is a symmetrical orbitals. Why I should have A1G is the most symmetrical.
No, but A1G are symmetrical, but it's directed mostly along C direction because it's kind of octahedral on phase, so that's in C direction.
Okay, I think the question is what means very anisotropic here. In the metallic phase, I still have substantial occupation of the A1G. But I mean, I agree with the question. Yeah.
I don't know what F is, but aren't we seeing from this picture that the Fermi velocities are pretty much the same?
I'm sorry.
The two directions, the Fermi velocities,
Yeah.
they look pretty much the same to me. Where that band crosses
okay.
Isn't one in the plane and one along the z-axis?
No.
No? I don't know what F
I
is.
don't remember.
Okay.
Okay, just to show you how this corresponds to the picture I've shown you before. So if you integrate here all the spectral weight, so this is the little A1G band here, which gives you this part of the spectral weight. And then you have this EG spectral weight here, and the Hubble band, which is EG parameters.
So for A1G, you have no Hubbard band?
For A1G, you have practically no Hubbard band because you're regularly decoupling. So the picture that we have actually, if now you close your eyes and you forget about the fact that quasi-particles in the EG are very badly defined, we just do a linearization of the self-energy in a Fermi liquid form, and then we actually plot the band structure where we put this self-energy, that's what I call linearized bands, and I compare that with a band structure where I first dehybridize the orbitals and then shift up the A1G orbitals. Then we see that actually we have a quite close correspondence. So somehow, to zeros order, you could say the metal insulator transition, this picture corresponds to when this band is sufficiently pushed up to get empty, and the EG pi here are then split by the Hubbard interactions into lower and upper Hubbard.
I have two questions. Do you see by this picture the difference occupation number before transition takes place? I mean, in the insulating phase and in the...
Yes, yes. And it's always a tricky thing to compare with experimentally measured occupations because you have to have the same orbitals, but to within what we can say, this corresponds. Okay, so that means in this picture actually, the essential ingredient is that correlations enhance the crystal field splitting. The eventual insulating phase would be run with a half-wave EG pi system. And in the metallic phase, we have this observation of orbital selective coherence effects, where the EG pi should be much more incoherent than the energy. Okay, how much time do I have left? 2 minutes. Okay. So then I can just give you a short flash on my last topic here, where comparing 4D compounds with 5D compounds, and knowing that you have learned, well, strong correlations in particular reside in the 3D and 4F, because these are the ones which don't have nodes and are most localized around the nucleus. You would expect, well, what would you expect? That this one should be least correlated. Okay, what you see here is the inverse. Strontium bosonate, already well discussed in this conference. Strontium rhodate are nice metals, whereas strontium pyridate is an insulator. But since you attended Natasha Perkins' talk, you also already know that don't get tricked by the 5D, where you can have actually where you can have interesting effects due to spin-orbit coupling. And so I want to advertise the poster by Cyril, that's the original out there, who has looked into how do the spin-orbit splitting and the correlations collaborate together here to form the splitting. Let me first tell you about the phase diagram somehow. As a function of temperature, this compound has a low temperature phase insulating with a well-tended antiferromagnetic order, and then at 240 Kelvin transition to a paramagnetic insulating phase. And what I will focus on only in this talk is here this. Again, there are some distortions. So the basic structure is the one that you would also have for the rosonates or for the lanthanum 2 copper 4, but then you have rotations of 11 degrees around the axis here as a function somehow of the different planes. You see the 0 plane equal 1/2, quarter, 3/4, and so on. So you have distortion is essentially consisting in a rotation of these octants. Okay, Natasha showed you that when you start from the L quantum number here, you split it in a crystal field, or you split it with crystal field here, or you split it with spin orbit, or you split it with both. You can end up. Sorry, this is not very visible. You end up with what I'm interested in here, an effective level G effective 1/2. W degenerate, Kramers degenerate only, and the effective J effective 3/2 levels, where you have Mg plus minus 3/2, Mg plus minus 2. So among the 3 T2G states, now we are splitting somehow into 2 states here, 1 state here, or with the quantum degeneracy properties here, two states here. When you look at the band structure of this compound, and this is actually down here, you realize that, okay, this is essentially the result of these two factors I told you, once spin-orbit splitting and once the distortions. How does it happen? Well, take just the undistorted structure, so assume strontium iridate has a structure as quantum ruthenate, and drop spin-orbit interactions. Then you have a band structure which is looking quite familiar if you know the ruthenates. Now you add the spin-orbit interactions, and you realize that at all these nice band crossings, you open little gaps to separate the bands here. You go back from here, and you add just the distortions. Well, you are, of course, multiplying all the units by 4. You have more bands. You have a little bit smaller bandwidth here. You add both spin-orbit and distortions, and you get a band structure here, where, well, quite suggestively, there's one band which is plotted a little bit lighter. Actually, it's 4 band, but it's just because you have 4 atoms. And which is kind of higher up than the other two. So the question that has been asked, and actually already here in the papers here, Kim and so on, was can we consider this as an effective G1/2 one-band? So to do that, let me, or to check this, let me plot the projections of the band structure on the G effective 1/2 and G effective 3/2 states here. What I realized then that indeed here this upper branch is the one that is mainly G effective 1/2. However, there is some leakage coming in here. For example, this is a G effective 3/2 and not 1/2. And so that means the rough correspondence between these plot here is existing, but for example here it is not G effective 1/2 anymore. So you have a system which looks like one band, but not really one orbital in that representation. Okay, so now we go to the EMFT results. We plot the spectral function, and here we plot a function of K again, with formula over here, in a color-coded fashion. So black is no intensity, blue is a little bit more, and then red, orange is getting sharper features. So here you have some rather well-defined features. Here you are opening up the gap. So now our compound is indeed insulating. And we can analyze now where these spectral features come from and what this corresponds to. And what we realize then is that if I plot the spectral density corresponding to the 2 3/2 orbitals summed up, I can stop at 0 because the empty states, there's nothing. So these orbitals are completely filled. The G effective 1/2 orbital now has a half-filled one orbital behavior in the gap in the middle. Okay, so now when Siri got this, we were very happy, but then I was asking strontium rhodate, what is now different? You have a 40 compound, but isostructural, isoelectronic. Why should that be metallic then? Okay, you did the calculation, and what's coming up, indeed, it stays metallic. It stays metallic with just one orbital which is completely filled, and 2 orbitals which actually survive at the front end. So that corresponds also to what was argued here in these papers by Haberkott and you based on LASU calculations, namely that one band is pushed away from the terminal and you're ending up with an effectively polarized metal with 2 orbitals. Okay, so what we are arguing here is that the paramagnetic phase.
Why the difference? It's a different value.
Okay, yes, okay, why the difference, of course, yes. It's actually going back to a quantitative difference in the parameters. You have a difference of the spin orbit, which is substantially smaller, so about 0.16 in the rhodate and about 0.4 in the iridate. But that alone is not enough. The other thing that we realized also, that in this effective T2G model, interestingly, the U for the rhodate is substantially smaller. And this seems to come about from the fact that the oxygens are higher in energy. And if you calculate the effective Hubbard interaction by screening, calculating the polarization really from the aldehyde band structure, we realized that the fact that the oxygens are higher in energy gives a better screening. So the U is indeed reduced in the C2G model. If we artificially push them down, we find that you would increase U again, and eventually you could also, when the critical U is a little bit lower.
Significantly smaller than in glutamate, but not in iridate.
Well, the mu in the rhodium compound was for F0 of 1.6. So it's substantially smaller than in the iridium. Interestingly, the U of the ruthenate and the iridate is not so much. Okay, no, actually, let's do this right. So what we're arguing here is that we have a paramagnetic, or that in the paramagnetic phase, we don't really have any either orbital or spin order, by definition, paramagnetic spin order. But we have what I would like to call the spin orbital order. Namely, we have the whole charge, or the whole missing charge, the whole, in the J effective 1/2 orbital here. And these are completely flat. So kind of, well, if you want to call it spin order. But again, in the paramagnetic. Okay, then I come to my conclusions. I've shown you how the enhancement of crystal fields by correlation can effectively suppress orbital degeneracies. And in the series of the D1 peroxides from the vanadates to the titanates, you go effectively from a completely degenerate 3-band model in quantum vanadate to an effective 1-band model into a titanate, and that decreases the critical U, which makes the compound insulating. I've shown you that similar mechanisms are coming out here in the comparison of the iridates and the rhodates. The iridium compound is ending up an effective 1 orbital model, or 2 spin orbital model to be precise. And I've just discussed how in vanadium 2 or 3 we believe that an effective enhancement of the crystal field splitting drives the metal insulating condition between the paramagnetic metal and the
can we drive the metal insulated transition by some external perturbation, for example, by magnetic field? Because that will disturb the structure very much.
Okay, good question. That requires, as we discussed, some more calculations. What we can say at this stage, just based on this calculation, that indeed this insulating state should be quite delicate. For example, what we tried is if you do LDF-free calculations with the given U that we believe is the correct one, for a phase where you only have distortions, or you only have spin orbit, but not both together, you would be metallic. So that would mean that, okay, with the magnetic field I can't answer, exactly. But if you, for example, if you grow it on a substrate, which would impose some lattice constant and impose some undoing of the distortions, we believe it should be metallic. Should really be fragile state.
I have one very general question to the very beginning. If you could show the very first phase diagram, non-general covered model with the question I asked already several times, and I still didn't get, this one. I didn't get a good answer, maybe you know. Okay, looks like critical temperature.
Yeah.
And critical point is for the, say, 0.04. So it's 2 orders of magnitude smaller than T or G themselves. Why is it really such a small parameter? I would expect that it should be something of order of 1. Just parametrically. So I don't see any small parameter. It looks like it's strongly suppressed from both T and D. And actually that's also experimental point. Because typically, you know, this vanadium oxide, for example, energy gap is maybe 0.6 eV on V2O3, so 6,000 Kelvin. And critical temperature is 150. Very, very far from standard BC.
Okay.
So why such a small value?
Okay, first remark is we should not really take this phase diagram, right? But we should take the one really with orbital degeneracy, which is not coming out.
Well, maybe that's factor of 2. Okay. Square root of n, it's not much. It's still 0.04, it's not something of order of 1. So where these two orders of magnitude come from?
Okay, so for example, if we take it, well, okay, we have at least a certain factor.
No, 1 order of magnitude.
Second thing, of course, is this is a phase diagram with a purely local effect, so I would expect.
Don't let them get in.
But okay, even in this simple model,
Yeah.
that let's forget for a while real material, but in a simple model, why isn't it something of order of 1? I don't see any small parameter.
Why in the local model you would expect it to be other one?
Well, because there is no other energetic parameters. I have only one parameter.
They need to get a right in person.
And if I have a separation of this energy by 2 orders of magnitude, almost. Of course, it may be something like 1 over 2 pi over q, but it would be strange. Maybe there is some physics in it. I think we don't know. Maybe not. Maybe it's simply numerical. I just wonder whether there is any physical reason which will make critical temperature much smaller than all energy parameters of the field. Not a quarter of bandwidth, a quarter of 1. Then I would expect the critical temperature to be also of the same order. And these 2 orders of magnitude small.
Okay, let's have a coffee discussion on that. I'm not sure I can say anything intelligent here.
But
could you give us a bit of insight on where you expect this LDA plus DMFT to work well and where you expect it to break down?
Okay.
You already said ordered phases, okay, but...
No, I'm not saying it's breaking down in order phases. I'm just saying in an order phase, you should, in your calculation, give the system the possibility to order.
Yeah.
So this is what we explicitly suppressed here. Okay, why? Okay, so let me start with the order phases and then we take the question more general. If you want to describe an ordered phase, and okay, no, if you do the calculation here, right? So we have learned in Matthias Reuter's lecture that what you're doing is you are associating to your correlated orbitals an impurity model from which you calculate a self-energy that is then used in the lattice or here in the solid. So now this self-energy, you have to give it some spin structure if you want to describe, for example, a ferromagnetic iron or nickel or whatever. You can do that, you just have to include it in the calculation. So what we did here is impose that the thing is ferromagnetic, search for the ferromagnetic solution of equations. Okay, so this is not a fundamental restriction if you look at it on the local level. Nevertheless, of course, we are throwing away non-local fluctuations, and whenever this is important for magnetic, whatever long-range order, so we don't have this. So having said this, of course, you can also go back and say, we are doing here a mean field calculation, calculating something as a local quantity, which in principle should have k-dependence. So the question you're asking then is, in which situations is the k-dependence expected to be strong? Okay, so we know, for example, in 1 dimensions, there's no point in doing local approximation. You can argue in 2 dimensions, all the important Q-rate physics, you will certainly need at least some non-locality of your self-energy. You can convince yourself, for example, that if you just stick to the purely local picture, you would have a purely K-independent quasi-particle residue. This is what we know is not true, for example, in group rates. So if you're in no-dimensional systems, you're not expecting the DMFT, let's say, to give you the final answer. At least not in regimes where you're relatively strongly correlated. Okay, if you go to more 3D systems, strontium-vanillate, for example, my belief is that it's not so bad. Strontium-vanillate, you have a kind of funny check, namely, by the fact that if you have a completely degenerate system, which is true for the 3 T2G states of strontium-vanillate, and you have Fermi liquidity, then this tells you that on very general grounds, the density of states on the Fermi level should not change if your self-energy is purely local. So kind of the comparison with the photo emission for this quantity would give you a hint that the purely local self-energy is not solar. Okay, I'm not sure I have answered to the question.
The iridate is magnetic insulator, right?
The iridate becomes magnetic below 240 Kelvin. This is not what we considered yet. Yeah.
So yours is the above the T
Yes.
and
We voluntarily have imposed paramagnetic states, so we have looked for the paramagnetic state.
so there will be a three transition then. There will be a paramagnetic metal and then paramagnetic insulator, and you become magnetic insulator.
No, sorry. The strontium iridate, the paramagnetic phase is insulating.
Yeah. I'm talking about the experiments. Because you are saying that, above the T-Nel temperature, it's a paramagnetic metal.
No, insulator.
A paramagnetic insulator, sorry.
You're
Yes.
talking about
So,
iridate.
yeah, I'm talking about iridate, strontium iridate, 214. So above that temperature, there will be a paramagnetic metal then. In the experiment, do they see activation behavior above T-Nel?
There's no sign in experiments for metallic phase in iridate.
Yeah, so I'm asking, like in the experiment, I think that there is a paramagnetic metal and then magnetic insulator. No? No, there is a paramagnetic insulator in between, and they see an activation behavior then?
Yes.
That's very different from what I understood. Anyway.
No, to my knowledge, there's no paramagnetic metal phase seen in the iridate. Rhodium is a
This
metal.
one, I don't think in this one there is any.
So they have this activation all the way to very high
Other
temperature?
compounds, okay, but the 214 is an insulator, paramagnetic, and contrary to what has been claimed in some theory. But in the experiments, to my knowledge, there's no evidence for that.
I don't think they have activation. They have power law looking like, but anyway, that's it. It's very close to metal insulator transition. I mean, you can tell because 113 is metallic. And as you said, even Natalia said that it's very fragile.
There's optics experiment tracking the gap. The gap at room temperature is 0.24 electrons. There's no way of telling it.
Can you tell us a little bit about how you calculate the U in the LDA plus DMFT? I'm still interested in this.
Thanks for the question.
And the motivation is that sometimes I see papers which seem to disagree with each other, and I wonder how ab initio this procedure is.
Okay, I can tell you exactly what we do. And okay, when you look at, say, the completely screened Coulomb interaction in a solid, you know that you can principally get it from the bare Coulomb interaction by screening it by your polarization function. So this is your screened Coulomb interaction W, screened by the complete polarization. So now, what we argue is the following. When I go to an effective low energy model, I have some of the screening processes still included within this model, and some I have thrown away in the renormalization groups, and somehow I should effectively include them in my parameters. So that means U in our approach here is a partially screened quantity which should be screened by everything that I don't keep in my model later on. So now, what we do is we attempt division of the total polarization into the polarization that would still be carried within the effective low energy space, and the rest. So now, what we want to call U is a quantity which is screened by this one, but not by this one. Okay, you do two lines of algebra and you find that this line here is an identity if you define this WR as a quantity where you screen the bare Coulomb interaction just by PR, just by the rest polarization, so to say. The resulting WR has the property that if you plug it in here and you screen it by the remaining degrees of freedom, by the ones that you still have in your model, then you would come back to W. So that is a motivation of saying that WR should be the thing that we want to identify. It has the right property that if you screen it further, we would come back to the completely screened Coulomb interaction. So what we call U, precisely, is the matrix elements within our linear functions constructed for the model that we are considering of the static value of this WR.
So How do I understand that two different LDA plus DMFT papers give different answers?
Okay, now
What is
tell
likely
you
to be the
exactly
problem?
which one, but
Oh, I can't do that.
Okay, so
Yeah.
if I take U as a parameter, which has long time been done, and in this first work that I've shown you, we have done that ourselves. Of course, then two different calculations should only give the same result if I have put in the same parameter. So the question, okay, so I'm aware of that for some systems there has been, for one and the same compound, completely opposite conclusions somehow, but for the 1111 weak sites, we trace that back really to a different choice of the parameters. So you define differently your model, you put a U as a parameter, and we can reproduce the calculation, but we don't believe that you should put those values of U.
You mean a different choice of the low energy parameters?
Yes.
I see.
So we were puzzled ourselves, but at the beginning, because we were thinking there's something wrong, but it's not. It's just LDA plus DMFT cannot be better than what you put in. So if you put in completely different things, you get completely different answers.
No, but I'm sorry, but you are calculating self-consistently or ab initio substance.
But I'm doing here, okay, then we calculate this thing here, the PR, from the random phase approximation. So this is not a self-consistency.
Okay. But you could do the same thing for J or J prime?
Yes.
Yes.
Yeah, we do it.
You do?
Yeah.
Yeah. Okay.
So you get in principle the full matrix.
Okay.
And the question afterwards, however, is how do you treat this full matrix? In principle, it's more information than you want. So what we do is to take the full matrix, fit it to a Slater parameterization, F2, F0, F2, F4, and then plug this in the calculation. So, I mean, I'm not saying this is the ultimate answer, but it's a well-defined procedure. And in a system where the influence of the rearrangements in the low energy space does not feed back too much on this PR, and after all, it's precisely the low energy space where things rearrange that you have cut out, it should be a reasonable procedure. Okay, however, I can maybe add one remark. There's one delicate point. So here, we put the static value here, and in everything I have shown you, we just treat this. What we did more recently is to check really what happens if we keep the frequency dependence of the U, and that has indeed substantial influences. So we recently calculated actually the barium 1 to 2 with the full frequency dependence of the spin cover.
Quick question?
Yeah, I think it's very thing because you more or less answered that I did not understand. With LDA plus DMFT,
Yeah.
can you predict magnetic orders? Can you compare two different orders? Or can you just give the bond structure for a given magnetic order?
Okay. Conceptually, you could give the system to choose its order, but of course you have to be careful what is your ingredients, because you probably, for some things you want to see, you would need certainly the cell energies in the cell factors. So in principle, you can choose your unit cells such as to choose the order which, to the extent that it's contained in the local physics, would then come out. Okay, in practice, it's of course a much simpler task to search for a specific order, to impose somehow that, for example, your cell energy on site A is to spin up is equal to your cell energy on site B to spin down, and calculate it. Conceptually,
Well, I just would comment on this. One can calculate energies of different states and compare them as
In
L
principle,
days plus U. And so this chooses then the order.
in principle, yes. But of course, it's heavy calculation, so that's not too much.
So I think we should stop here and thank